In this video, we're going to talk about finding the arc length of a curve. So I didn't end up getting a picture of the actual function all by itself on there, but the idea is we're going to take this function here and find the length of that curve. So literally if we walked along that graph, how long would we walk? So what we're going to do is what we always do in 252. We're going to take our curve, we're going to chop it into a bunch of little pieces here. All of these are going to have a width of delta x, and we're going to approximate the length of that sort of rounded curve with the straight line connecting, say, x sub 0, f of x sub 0 and f of x sub 1. So we'll connect those two endpoints of our intervals with a straight line and use that distance to approximate our arc length. And so what we'll do is take each of the lengths of these orange lines that we're highlighting there, and we'll add up all of those lengths, and that'll give us an approximation to our curve. Now, just like any other approximation that we do, we're going to have places like right here in that second interval where our straight line is going to approximate our curve line really, really well. But then also we'll have spots like in our first interval where that approximation is not so great, but that lends us to kind of looking a little bit more closely at how we're going to figure out what that length is of this orange line there. And so what we're going to do, so here's kind of, this isn't exactly that function, but it's the idea of what we're going to do is that we're going to look at that first endpoint and those last endpoints, and we're going to make a straight line connecting those two. And we're going to look at finding that distance. How long is that straight line? Well, to figure that out, we need to get this x length here and this y length here, because this makes a right triangle. And just to kind of recall a little bit, that right triangles have that Pythagorean property that the two shorter sides, if we square each of them, add them up, we get that longer side squared. And this leads us to our distance formula. If we're looking at the distance between 2 points in the plane, here's the distance formula. I never make my square roots long enough. So the idea that we're looking at right here is this point is, say, our x1, y1, and this point right here is our x2, y2. And so this amount, our delta x, is the same as what we would get from doing x2 minus x1. And this amount here, our delta y, our change in y, is what we get from y2 minus y1. So we're just going to relabel these in the distance formula to get that length. So our length is going to be the square root of that delta x squared. And we're going to use just plain delta x here because each of our intervals, they have all the same delta x. So no matter what two x values we pick to find that change in x, we're always going to get delta x. What is going to be different depending on which interval we're in is the delta y. That change in y, it's going to be different. Like here we're going to get a positive number, here we're going to get a negative number on that second interval. So that's going to be different. So we'll put a subscript on that. So now we're going to rewrite this a little bit more. We're going to do a couple little kind of tricky things. I'm going to factor out of this expression that's underneath our square root. I'm going to factor out a delta x. So what I'm doing here is that I'm just, factoring that out. So if I multiplied this back through, we get exactly back where we started. To kind of show you, with a little bit of a kind of extra example here, the idea is that maybe we have 2x plus 4, and when we factor out at 2, that we're taking each of our terms and dividing that by 2. So we get 2 times x plus 2. So we factored out that 2. So that's what we're doing here. We're factoring out that delta x. So we're going to take each term and divide it by, or delta x squared is what we factored out. And so we're dividing each term by delta x squared. And now this we can simplify because we can break this up since we've got multiplication inside of our square root. And we can separate out that delta x squared that's out in the front, and we have the square root of delta x squared, so that's delta x. Now at this step here, I want to look at this delta y over delta x. And remember what that is. That is literally our change in y divided by our change in x. And this will feel really familiar because it's a couple of things. It's the slope. And remember, slope, we get that from our derivative. So this is going to be approximately the derivative of our function at that point. So that's one way that we can find that, what that slope is. So you can kind of think about that. We know that somewhere by the intermediate value theorem, that somewhere in here, we do have a point where we would exactly get that slope. And so that's the derivative that we're using there. So we can replace that delta y over delta x with that it's the derivative of our function being squared. So if we take a look at this, this is how we're going to get each individual length. And then what we want to do for our arc length is that we want to find the summation from 1 to n of this square root, and I'm purposely going to move that delta x to the back. Oops, get my other bracket in there. Again, never make that long enough, do I? That square root. And then times our delta x. And so this should look familiar. And what we want to do is what we always want to do with this is take the limit as n goes to infinity. So again, back up at our picture, we want to make those intervals smaller and smaller and smaller so that our derivative is going to give us a better approximation of that slope. And if we make those intervals smaller and smaller and chunk this up, this is going to be equal to our integral from a to b of the function, the square root of 1 plus the derivative of our function squared, and then delta x turns into dx. So this is our formula that we're going to use to give us the arc length of a function. So I did also grab the theorem out of the textbook. So this is, we've got y is a function of x, and here's our arc length. So it's really just a matter when we're using this, for example, if we want to find the length of the natural log of cosine of x from 0 to pi over 3, we just need to find this integral. So the way that I like to do this is to really break it down piece by piece. So I'll usually start with just finding what the derivative is of this function. So it's going to be 1 over cosine of x times negative sine x using our chain rule. And we get negative sine of x over cosine of x, or negative tangent of x. Then I'll actually, take the step where I square it, because the reason why I do this sort of piece by piece is that it's a lot easier to see how I can do the simplification if I take it piece by piece versus trying to shove it all into that integral right at the beginning. So this is going to give me positive tangent squared of x, because I'm going to have a negative number times a negative number, and that's going to give me positive tangent squared of x. And then I'm going to do the square root of 1 plus, so that derivative squared. So I'm going to be plugging that tangent squared that we got into this square root. And so again, I'm just trying to simplify this as much as I can before I actually do the act of taking the integral. And some things to remember. Remember, we have our trig identities. We've got the one that says that 1 plus tangent squared of x is equal to secant squared of x. And so we can replace our 1 plus tangent squared of x with secant squared of x. And we're square rooting something that's being squared, so we get secant of x. So our arc length is now going to be the integral from 0 to pi over 3. We've done this whole part right here. So again, this is the function that we're taking the integral of. So the function that we're taking the integral of is going to be secant of x in this case. Now, this is not one of the integrals that seems like it should give us a nice easy function. It doesn't really, but I had to go to my table of integrals to find that this is the natural log of secant of x plus tangent of x, and we're going to do this from 0 to pi over 3. And now it's just a matter of using our fundamental theorem of calculus. So you get to watch me write here for a little bit. Super exciting, plugging in pi over 3 and then plugging in 0. Secant of 0, tangent of 0. There we go. So with the first one, we get the natural log of 2 plus the square root of 3. I can lose the absolute values because both of those things are positive. And then minus, we get 1 from secant of 0 plus tangent of 0. So natural log of 1, that is 0. And so we get the natural log of 2 plus the square root of 3, and this is approximately 1.3170. There we go. And I wrote this to 4 places because Newton Alta is going to have you approximate a lot in this section, and 4 places is usually what it asks you for.